Hi, in this lecture we're going to talk about work and energy. So we're going to physically define what we know about energy and then move on to establish a connection between energy and physical work. Alright? So naively, one can define energy to be the ability to make things move. So why is it a naive definition? Because energy is very abstract thing. Energy, you feel energy, you use energy, but it is very hard to actually put a definition on energy. All right. For example, when you have certainly made this remark at some point in your life, say for example on a moving day, you say to your friend that I have to push this desk so far. So what are you actually implying by that? Unknowingly, you're actually speaking physics when saying that you're pushing something. Push is a kind of a force, and you're pushing this desk so far, meaning you're establishing some distance. So you're applying a force over a distance. This means that there's a connection between force and distance, which we want to establish to really get an idea of what energy is. Why? Because when you apply a force and make something move, you're actually spending energy doing that. And then if you spend energy, you are actually working. So there is a connection between energy and work, which we want to establish. In physics, whenever we want to establish connections between quantities, we have to set up an equation. Force and distance are indirectly connected through kinematics, because force is, as we know, is a cause of acceleration, and acceleration is a kinematic variable, and distance is a kinematic variable as well. So they're indirectly connected. Now we want to establish a direct connection between force and distance, not via acceleration. So to do that, we have to start with kinematics and use Newton's second law in it. We need an equation with acceleration and displacement in it, because force is the cause of an acceleration. So we start with this equation, Vf squared equals Vi squared plus 2ax, but we remind ourselves that the Newton's second law states that the net force on an object is equal to its mass times the net acceleration. So the acceleration that the net force causes should be equal to the force over m, the net force over m. So wherever you see a in this equation, replace a with F net over m. We do that, and we want to separate out F and displacement, because we want to establish a connection, remember, between force and distance. So when we do that, we want to rearrange our equation such that force net times delta x is on one side and everything else on the other side. So we have established a connection between two things. One is the product of force and distance or displacement, which is what you were actually telling your friend. You're applying a force on something to make it move. So you're actually saying that there is a product of force and some distance. This is equal to something. What is this something? This is something we call change in K. What is change in K? Delta is, as we know, we have met delta before, is a change in anything. K is a new quantity that we have just learned. It is the kinetic energy, or the energy associated with motion. Anything moving will have kinetic energy, and it is defined as 1/2 times mass times the speed squared. So kinetic energy is possessed by anything that is moving, and the change in kinetic energy is equal to the net work you do. And what is the net work? Work is then defined as the product of the net force times the distance or displacement. Distance, when we talk about only the magnitude of displacement, is the distance. However, work net is just the product of the two things, force and delta x. All right. So far, we have naively defined energy to be the ability to make things move, but now we want to set it on a more solid footing. So what we then ask is, how does it work? Because it is so hard to define, let us not ask what is energy, but let us just know or experience how energy works. Okay, so energy works by transfer and transform. For example, when you take some food, all right, let's say you are eating an apple. The apple is transferring its chemical energy into you. Okay, so you are actually intaking chemical energy. When you run or walk or make something move, that is, do work, you are transforming this chemical energy into some other form of energy. When it is involved with motion, it is called kinetic energy. All right, so you take chemical energy from food and you transform it to kinetic energy. As we have just seen, that energy is being transformed from one form to the other. However, we have not really created or destroyed any form of energy. We take some energy from the apple and we use that energy up when we are running and walking or doing anything, right? This then gives me the law of conservation of energy, which tells me that energy can neither be created nor be destroyed. It can only be transformed from one form to the other. All right, so the total energy in the universe is the same from the beginning of time to the end, whenever that end may be, or maybe the world has ended by now. But it cannot be created out of nothing. Energy cannot be created out of nothing, or energy cannot be destroyed into nothing. All right, it can only be transformed and transferred from one object to another and one form to another. All right, so this is a universal truth. All right, now let's talk more about work. We have investigated our equation between merit, force and distance, and we found two quantities. One of them we defined to be the kinetic energy. The energy defined the energy that is related to motion. Whenever any object has motion, that object has kinetic energy, and change in kinetic energy was equal to the work done, the force times distance. That was the total work on an object is equal to the net force on it dot delta x. In physics, this dot does not mean normal multiplication. It has different implications, all right, but we'll not get there today. This network can be positive or can be negative. Since network, as we said, was equal to the change in kinetic energy, that change can be negative or positive. It doesn't mean it is denoting a direction or that work is a vector or something. What this just means is that if you take energy out of a system, then the network would be negative. If you put energy in, that network would be positive. All right, so for example, if you're pushing a box, you are giving energy into the system. When you're doing work on it, work on the box, that work would be positive. However, the ground has friction, so if you're dragging or sliding the box along the ground, then the ground will work to oppose you. So it will take away energy from what you're giving it in, because as we have just seen, energy is the same, but it is just transformed from one form to another. All right, so you are pushing it, the friction is pushing back, so it is taking away some energy. That is why the work done by that friction would be negative. This is a very simple example. We will investigate more mathematical ones soon. Also, the net force and this change in displacement must be in the same direction. Why? Because as we know from Newton's second law, F equals ma, the net force will provide or produce an acceleration in the direction of the force. Whichever way the net force is pointing, the acceleration will be pointed the same way. Hence, as a result, the motion produced, the displacement produced, must also be in the same way as, or same direction as, the net force. So we can understand it by looking at each force on an object. As we know that there are multiple forces acting on an object, we will investigate each force on an object and then check it with the direction of motion it is producing. For example, if you have a force that is at an angle of some angle to the displacement being produced. So for example, if you are attaching a rope to a box, say a very small diagram here, there is a box here and you attach a rope and you pull it, okay, you pull it this way, so you're producing a displacement in the horizontal direction, but your force was somewhat along your vertical or horizontal at an angle. Okay, so there was an angle between the force and the displacement produced. Let's call that angle theta. Now the work done by that specific force would be the magnitude of the force, always positive, the magnitude of the displacement, which is the distance, always positive, times cosine of theta. What is this theta? Be very careful about this. This theta is the angle which the force in question makes with the displacement it produces. This is not the angle of incline or something that we have been talking about so far when we investigated masses on an incline moving up and down. This angle is the angle between the force we are investigating, which is causing some work, and the displacement that force is producing. All right, so be very careful about that. So this is a more complete definition or equation for work, which we use for each of the force acting on an object, and to find the net force we just add all these separate work done by all these different forces. Okay, now another property of work is that work is a scalar. So even though it can be positive or negative, this is just a scalar, and I have already hinted at why it is a scalar. You think about why it is not a vector even though it is positive or negative. The SI unit of work is joule, and joule is basically stems out from force times distance is units of Newton times meter. So Newton meter is the same as 1 joule. 1 Newton meter is the same as 1 joule. So joule is also the unit for energy, because as we have seen that the change in energy is the same as the work done on an object. All right, now let's look at an example. Here we have a sled or a box or anything which you're trying to move in the rightward direction, distance of 15 meters. By applying a force of 45 newtons at 30 degrees above the horizontal, as shown. Now we want to find what is the work done on the object. All right, so there are a couple of ways that I know how to solve this problem. One of them would be to start with our free body diagram and draw out the forces as we have done so far. Let's do that, since that is the way we know. Plus x plus y is our axis. This is the object in question. What are the forces acting on it? The object has a mass, even though we don't know what the mass is in the question. So the weight is mg. It is sitting on a ground, so the ground exerts a normal force on it. We can ignore friction just for now. And there is a force that you apply, which has a magnitude of 45 newtons, and it is 30 degrees above the horizontal. All right, that is our free body diagram. Now we want to set up Newton's second law. That's what we do when we are dealing with forces. That's the first thing that comes to mind. To do that, we have to break this force down into components, since our axis is not aligned with the force. So the component by now you should be pretty confident about looks like these. So this is Fx, this is Fy, and we know what the magnitudes of Fx and Fy are. Fx is the adjacent and F equals 45 is the hypotenuse. So Fx is 45 cosine 30, Fy is 45 sine 30. All right. Then we read the question again. The question says that the application of this force causes the box or sled to move horizontally a distance of 15 meters. Since there is no vertical motion, there is no work done by any of the vertical forces. But we can go ahead and check if that's the case truly. So how do we do that? We remind ourselves what is the definition of work. Work for a particular force is equal to the magnitude of that force times the magnitude of the displacement produced by that force, which is the distance, and the cosine of the angle between that force and the displacement of the object. This is the definition of work. Let's use this definition and investigate each of the vertical forces first. So in the y direction, what are the work done by all these forces? Let's check if they're indeed zero, since there is no motion in the y direction. First, go ahead and check weight. The work done by gravity, right? Because weight is nothing but the manifestation of gravity near the surface of the earth. Put it in the definition of work. So F, magnitude of F is just mg for gravity. So mg times the magnitude of the displacement produced by any of the force. So the total displacement produced, the total displacement of the object, which is 15 meters. And then cosine of theta. Theta is important. Theta is the angle between that specific force and the displacement of the box. So we can see that, let's draw it on our free body diagram. The magnitude or the displacement, the displacement is in the horizontal x direction. All right. So this is a displacement of 15 meters. As we can see that weight is vertically down while the displacement is horizontally 15 meters. The angle between the weight and this displacement is 90 degrees. So theta for the weight is 90 degrees and cosine of 90 is 0. So the work done by gravity is also 0 joule. Right? So one of the vertical forces checked. Let's look at the normal force. Work done by the normal force is the magnitude of the normal force. Let's just write it as n for now. And then the displacement, which is 15 meters. And then cosine of theta. Cosine of theta. Again, n is a vertical force, displacement is horizontal, so the angle again is 90 degrees, cosine 90 is 0, so the work done by the normal force is also 0 joule. Checked. Now we have a third vertical force left, Fy. Let's check the work done by Fy. Fy, the work done by Fy is the magnitude of Fy, which is 45 sine 30. So 45 sine 30 times the displacement, which is 15 meters, the magnitude of the displacement, which is the distance, 15 meters, times cosine of theta. Now theta is again the angle between the force you're considering, in this case which is Fy, and the displacement. So the displacement is horizontal as before. So the angle again is 90 degrees. So cosine 90, this is again 0. So the work done by the y component of the force you're applying is also 0 joules. So in fact, all of the vertical forces produce 0 work, since the displacement is not along the y direction. There is no displacement or no component of displacement in the y direction. All right, so the work done is 0. Then the only force that does any work here is the x component of F, which is Fx. So the work done by Fx is equal to the magnitude of that force Fx, which is 45 cosine 30 times the magnitude of the displacement produced on the box. This is 15 times cosine of theta. Now theta is again the angle between the force you're considering. In this case it is Fx and the displacement. So displacement is horizontal, Fx is horizontal, so they are parallel to each other. For two parallel forces, the angle between them is 0. So cosine 0 is 1. So the work done is non-zero by the x component of the force you're applying, which comes out to be around 585 joules. So this is the work that you do to drag this box horizontally a distance of 15 meters. Now let's look at a more direct method to directly calculate what is the work done by the force that you're applying to drag this box a distance of 15 meters. All right, so we know the definition of work is still the same. It is magnitude of the force you're applying times the displacement x, the magnitude of the displacement, times cosine of the angle between F and delta x. Now the work net would be the net work produced by the net force, right? So what is the net force on this object? We can see that there is no motion in the y direction, because it just tells me that this force makes the box slide horizontally. So there is no net force in the y direction, and as we have checked, there is no work done in the y direction. So we can just look at the diagram and say, and investigate the question and say that there is no direction, no motion in the y direction, hence there is no work and there is no net force in the y direction. The only unbalanced force on this box is 45 newtons. So this is the force, whichever component of this force that may be, this is the force that is causing the net work on this box. So we can just directly use the definition here to calculate it. So the work done by F would be the magnitude of F, it is 45 newtons, the magnitude of the displacement, which is 15 meters, and then cosine theta. Theta is the angle between the force being applied and which is causing the displacement and the displacement itself. Displacement is horizontal, force is making an angle of 30 degrees with the horizontal. So it is cosine of 30 degrees. This comes out to be directly 585, around 585 joule. So we can see that we can choose a longer path or we can choose a shorter path, but we have to be careful about reading the question. If the motion of this box was along both x and y, then it would be easier to go and use method 1. If the motion is only in one specific direction, it is better to just look at your free body diagram and pick the unbalanced force on it, because you can just tell by now, I hope, and then work out the work using the definition directly. All right, I hope this example made sense. In this example, we have the same block that we were sliding across the floor and applying the same force, 45 newtons, at the same angle to the horizontal, 30 degrees, but instead we are now considering the friction between the box and the floor, with the coefficient of both static friction and kinetic friction given to us as 0.03, and the mass of the box is given to us to be 55 kilograms. Our goal in this problem would be again to find the work done on the object. So let's go ahead and try and solve this. So we will use method 2, since we know that the displacement is just along horizontal direction, so we don't need to check the vertical work done again. So let's start with a free body diagram. That's just a nice practice. Plus x plus y, you have the block, the weight is now 55 times g, the normal force this way, the force of, that's a bad straight line, force of 45 newtons going this way at an angle of 30 degrees. And now in addition to that we have friction. So friction will oppose sliding. Since you're moving in this direction to the right, friction will be, you're sliding in this direction, this box, friction will be opposing that sliding motion, so would be pointed towards the left x-axis or the negative x-axis. This is our free body diagram. Now let's get down and just write down what our work is. Remember, the definition of work was magnitude of the force times the distance times cosine of the angle between the force and the distance, call it theta. Alright, so what is the work done? By which of the forces does any work? Since the motion is in the horizontal direction, the vertical forces don't do any work. So the only two forces that are working is the total 45 Newton force. Alright, we are not considering just components here, we are considering the total 45 Newton force and the friction, because these have horizontal contributions. Alright, so work done by 45 Newton force, let's call this the work done by me. This is equal to the magnitude of the force, which is 45, times the distance, which is 15, times cosine of the angle between 45 and 15, the force and the displacement, which is 30 degrees, right? Because remember, displacement is in this direction. All right, this comes out to be, like we calculated, it's around 585 joule. The work done by friction, the magnitude of the friction, let's call it F, times the displacement, which is 15, or the distance actually, because we are taking the magnitude of the displacement, times cosine of the angle between F and delta x. Now F and delta x are pointed opposite to each other. So F is pointed this way, delta x is pointed that way, right? So what is the angle between F and delta x? It forms a straight line, so it is 180 degrees. So this is cosine 180. Cosine of 180 is negative 1. So the work done by friction is actually negative 15 times F. What does this negative mean? We have talked about the properties of work, and negative work just means that you are taking, this force is taking energy out of the system. So friction is taking energy out of the system. Now what is the magnitude of the friction? To do that, we have to remind ourselves that the magnitude of friction force is given to us as the coefficient of friction times the normal force. Since it is already sliding, we are talking about kinetic friction. Then we want to find what the magnitude of this normal force is. To do that, we have to write down Newton's second law in the y direction. In the y direction, what do we have? F of y is equal to m times ay. Ay is 0, there is no vertical acceleration. And what are the forces in the y direction? We have n, and we have the y component of 45, which, as we have calculated before, is in this direction, Fy, 45 sine 30. So normal plus 45 sine 30, they're both in the positive y direction, and then there's a negative weight, negative 55 times g, which is 9.8, equal to 0. Then normal is, the normal force has magnitude 55 times 9.8 minus 45 sine 30. This gives me a magnitude for the normal force as, let's see, 516.5 newtons. All right. Then magnitude of friction is mu times n. Mu k is 0.03 times 516.5, which comes out to be around 15.5 newtons. This is the magnitude, so no signs are involved here. Alright, so we take this magnitude and we plug it into the work done by friction. The work done by friction therefore is negative 15 times F. So 15 times the magnitude of friction, which is 15.5. This comes out to be negative 232.4 joules. This is the work done by friction. The total work done on the object by both of these forces, the net work, is equal to, the net means total, so you just add the separate works together. Two forces are doing work. The force exerted by me, work me, added to the work done by friction. No other force is actually doing any work on the object, as we have checked. This is then 585 minus 232.4 joule. This comes out to be around 352 joules. So initially, when we didn't consider friction, the total work was 585 joules. Now when we have incorporated friction into the problem, we see that the work has decreased. The total work done on the object has decreased. So friction has actually taken some energy out of the system, as pointed out by this negative sign. I hope this makes some sense.